So the last topic in this unit is that of pipe flow rate measurement. In a previous chapter, we saw that between any 2 points in a pipe flow, which is inviscid, in which there is no incompressible or compressibility effect, the flow is incompressible, and steady flow, one could apply the Bernoulli equation between 2 points that are connected by the same streamline. Okay. Now, in a realistic flow, there will be losses, and we are going to use the Bernoulli equation to derive an ideal flow rate first. That is, if you apply the Bernoulli equation and also combine it with mass conservation, which is A1 V1 equals A2 V2, one could derive the expression for the volume flow rate. In the ideal situation, we call it Q ideal. This would be A2 V2, or this would be square root of A2 times square root of 2 times P1 minus P2 divided by rho times 1 minus beta to the fourth, where beta is d2 over d1. This is the ideal flow rate that neglects any viscous losses or pressure losses. Okay, but a realistic flow is one in which P1 plus half rho V1 squared plus rho GZ1 equals P2 plus half rho V2 squared plus rho GZ2 plus the total losses, which are rho G HL. Okay, in this case, the flow rate can be calculated as C naught times the ideal flow rate that was derived in the previous slide, which is C naught times A naught times 1 minus or 2 times P1 minus P2 divided by rho times 1 minus beta to the fourth. Now, what is C naught? C naught is a coefficient that compares the true flow rate to the ideal flow rate. Usually it's a coefficient that's less than 1, and Q is measured. To get C naught, you have to measure Q, and Q ideal can be computed, and thus C naught is tabulated for us to use. Okay, C naught is tabulated. Now, a pressure such a setup would be, you have a flow going through Q, which is unknown. Okay, Q is unknown. You are trying to determine Q, and then there is a section that is added, okay, in which, let's say we insert 2 pressure taps, P1 and P2, and between the 2 taps we create a joint or a section in which we induce a pressure drop. We induce a pressure drop. Okay, this is by construction, and the fluid comes in. You can record what is the pressure drop that the fluid undergoes between 1 to 2. Between 1 to 2. The diameter is known, the fluid is known, okay, they are all known. The area of this minimum cross section A naught is also known or is designed, and A1 rho and mu are known or designed. Diameter is known. Okay, with all these parameters are known, and that was a software glitch. Let me try again. Okay, I'm going to start again from the first. So we start with a pipe through which there is a flow rate Q, which we aim to measure. Okay, this is to be determined. And then we drill 2 tap holes wherein we insert pressure taps that can record P1 and P2 or P1 minus P2. Okay, and in the middle section we introduce a flow constriction that is designed by us. That is, we know what is the area of the flow constriction, we know what is the area of the inlet flow, so we can calculate beta, which is d naught over d1. The density and viscosity of the fluid are known, and P1 minus P2, the delta P, can be measured. Okay, so with these values, you can calculate what is the ideal flow. Ideal flow is A naught times the measured pressure drop divided by density times 1 minus beta to the 4th. Okay, the Q real would be C naught times Q ideal, and what we need is a tabulation of C naught. What we need is a tabulation of C naught for various designs of the flow constriction. Okay, and this is provided in figure 8.39, 40, 41 and 42. This is provided in figure 8.39 to 42. Okay, we will use these in problems to calculate the velocity of the flow rate. There are 3 main types of constrictions that we have seen. One is that of orifice, in which the flow constriction is abrupt. You want to measure P1 and P2. The constriction is abrupt, A naught, A1. The other is that of venturi. A venturi is one you have a flow constriction that is gradual. Okay. We record P1 here and P2 at the throat, P2 or P2. Okay, and then the other is that of nozzle, where we have a flow constriction and then we tap P1 here and then there is a nozzle through which the flow accelerates and it is let out. The pressure is measured here, P2. Okay, so this is a nozzle. In all the cases, the equation remains the same, C naught times Q ideal. For all the devices, nozzle, venturi or orifice, the pressure drop may differ. Like for example, an orifice produces a very abrupt pressure drop. It gives you the highest pressure drop, which means more losses, which means more pumping power. The venturi gives you the lowest pressure loss, and the nozzle is somewhere intermediate. Okay, in terms of ease of construction, the orifice is very simple. It's just putting a plate in a pipeline and drilling a hole through. Venturi looks much more complicated. You have to do complex machining, which means more cost, but also it comes with lower pressure drops or lower losses, and nozzle is again intermediate. In all the 3 situations, we use the same modeling. The real flow rate through the system is the ideal flow rate multiplied by the venturi discharge coefficient. It's called C naught is called the discharge coefficient. And we will look at different types of devices or pipe flow rate systems to measure volumetric flow rate. Okay, and we'll see this through examples. And that concludes this unit. Thank you.